because it allows us to swap out algebraic expressions for trigonometric expressions. It's very beneficial because, generally speaking, it's not difficult to find derivatives and antiderivatives associated with trig expressions, simple ones anyway. Sine, cosine, secant, things like that. All right. So if I have a monstrous algebraic expression, I might be able to swap it out for something that's trig-based and then anti-differentiate from there. All right. So, but in order to understand it, we have to take a look at some triangles. I mean, there's some rules here. You get these right from pretty much every calculus textbook that exists. But let me show you where they come from. Because they're talking about integrals involving the square root of a squared minus u squared. That's Pythagorean in nature, right? So if I tell you that I have a triangle with some reference angle theta, a right triangle, depending on where my variable and my constant are located within that triangle, I can swap out some algebraic expressions for some trig expressions. So if I tell you that it's organized so that the variable part is vertically organized and the constant is on the hypotenuse, then the missing side would be the square root of a squared minus u squared. All right. So, and I'm just really kind of arbitrarily placing the a and the u, because really, if you think about it, there's three unique ways that you can place the a and the u on the triangle. Everything else would be a reciprocal of those values. So I can place it in this fashion, in which case, if I were to relate, because this is the key to everything, relate the radical part to the constant part, and you get a secondary equation, right? And that'll naturally define the trig function that goes along with it. So the radical part here happens to be on the adjacent side. And the constant part happens to be on the hypotenuse. Right? If I create a ratio out of that, so radical over constant, I'm looking at the adjacent side divided by the hypotenuse. That's the cosine function. Okay. Another way I could organize my triangle would be to have the variable part on the opposite side, the constant part on the adjacent side, in which case my hypotenuse would be a squared plus u squared under the radical. If I'm relating, again, the whole goal here is to relate the radical part of it to the constant part of it. Right, that's how we're going to make our substitutions. Take the radical part and divide it by the constant part. It'll naturally create a trig ratio, in this case hypotenuse over adjacent, which is the definition of the secant ratio. And the last really unique way of doing it would be to let the hypotenuse be the variable part and the adjacent side be the constant part, in which case your opposite side would be the square root of u squared minus a squared minus. If I divide the radical by the constant, it's the opposite side divided by the adjacent side. Opposite over adjacent is equal to tangent. All right. These relationships, and we're going to draw triangles for each one of the integrals that we're going to tackle on the next page. Each one of these triangles will dictate the substitutions that allow you to be able to integrate expressions that you wouldn't think you would be able to integrate. Question?
When you see like a problem, how do you know which is the A, which is the U?
The A value is going to be whatever the constant part of the radical is. The U will be the variable part. And I'll show you that in a sec. All right. So, oops. On the next page, we have a bunch of, well, they're all radical expressions, but they all look pretty nasty. And I don't know that you would necessarily look at them and say, well, that is clearly the antiderivative of an arc, involving an arc function, right? If you were to look at this and say that the answer is going to involve arc tangent, that may be because you're completely ignoring the 3/2, But that 3/2, whatever the power is, it's completely irrelevant. If you're looking at a Pythagorean relationship that's in binomial form, then you're looking at something that can be completed using a trigonometric substitution. So let's take a look at the first one. So we have a radical that follows the model, and I'll just write it up top. I'll just write it below, actually. It follows the model of a squared minus u squared. All right, which would lead us to think that the a value has to be equal to 3 and the u value has to be equal to x. All right, so we have an a value and a u value. What we want to do is construct a triangle with some angle theta that would allow us to place the a and the u, specifically the 3 and the x, in such a way that the remaining side will equal the square root of 9 minus x squared. So the square root of a squared minus u squared. In a lot of ways, it could be kind of trial and error until you feel it out and get a sense of it. If that's the case, you might say, okay, well, let me put the 3 here and the x there. If I put the 3 as the base and the x as the height, what's my hypotenuse going to be? Yeah, so that's not what we want, right? So let's get rid of those. If I put, let's say, the x here and the 3 here, what's my missing side going to be? Square root of x squared minus 9. Okay, so the exact opposite of what I want. All right, but if I put the, I'm getting ahead of myself, put the 3 as the hypotenuse and the x as one of the 2 legs, then I'll have exactly what I need. So I'll put the x here. My missing side would then be what? 9 minus x squared, aka exactly what we need. All right, so how is this beneficial? Well, the idea is I can take the ratio of the u over the a, so x over 3, is what trig ratio? Sine. Sine theta is equal to x over 3. All right. If I'm looking for the ratio, and this is the most important part, because getting the ratio of u over a is not too difficult, getting the other equation is a little iffy. You're looking for the ratio of the radical part over the constant part. All right, so radical 9 minus x squared over the constant forms what trig ratio? Cosine, because you're taking the adjacent side and dividing it by the hypotenuse. All right, these are going to be our substitutions, believe it or not. We just have to do a little bit of work. All right, first thing we're going to do is we're going to solve our sine equation, but we're going to solve it for x in terms of sine. So x will be equal to 3 sine theta, and then take its derivative. Dx equals 3 cosine theta d theta. After that, we're going to take our secondary equation. No calculus required for that. We're just going to solve it for the radical, right? Because that's the beefy part of the integral that we need to swap out. So I'm going to solve it for the square root of 9 minus x squared. And so we'll get square root of 9 minus x squared equals 3 cosine theta. And it seems like, okay, we did a lot of work, but where is it going to get us? Take a look at everything I wrote here in black and compare it to the the ingredients in the integral. I need a dx, I got a dx. I need an x, I got one of those too. I need a radical, there it is right there. All in terms of trig functions. All right, so I'm going to replace my dx with a 3 cosine theta d theta. I'm going to replace my x squared, so parentheses squared, with a 3 sine theta squared. And then I'm going to replace my radical part with just a 3 cosine theta. Clean it up. Not much to clean. I personally think, nobody agrees with me on this ever, but I'll say it anyway. I think it's easier to simplify fractions involving trig than it is to do it with algebraic components, because I generally don't have to worry about conjugates, factoring, things like that. I'm just looking for maybe an identity at worst. In this case, look, boom. 1/9 cosecant, I'm stealing my own thunder, sine squared theta d theta, which equates to 1/9 cosecant squared theta d theta. So you may wonder, okay, what's the benefit of changing from something that's in terms of sine to something that's in terms of cosecant? You may look at that and say, well, in algebra trig and pre-calc, it was like, well, we always went the other way. Why would we want to do that here? Do we know the antiderivative of sine squared theta? Do we know the antiderivative of cosecant squared theta?
Yes.
Yes. All right. So negative cotangent. So we're looking at -1/9 cotangent theta plus c. So the only thing that we're missing here, it's very subtle, very tiny. We're missing the part where it's in terms of x. Right? We substituted away from being in terms of x to get it in terms of theta. Now the original problem was in terms of x. I have to give an answer in terms of x. All right? Whether it's in simplest form or not is a different story. But very easy to do. And this is one of the main reasons why we drew the triangle. Looking at the triangle, can you tell me what the cotangent ratio is?
3/rad.
That would be cosecant. Opposite of tangent, yeah, rad 9 minus x squared over x. All right, adjacent over opposite. So once we bring it back in terms of x, we're in good shape. All right. Now, number 2 is very similar to the one that we did on the previous page using u squared substitution. We can kind of go after it with that technique if we wanted to, but you also notice that there's a radical in there, so you may look at that and say, well, I don't really like that too much. But we're looking at just the idea that we could identify a u and an a and create a triangle out of this. All right, so what we got from the last problem really is that the u is going to be the square root of the variable part. The a is going to be the square root of the constant part. So in this case, the u would be what? 2x. The a would be what? So what I want to do is create a triangle, place my u's and a's so that the missing side is going to be the square root of 4x squared plus 1. All right? And we want to try to limit ourselves. It could work with any number of, I mean, you got 6 trig functions to play with. You're not limited to the 3 that we talked about on the previous page, but those are the best ones to work with. They keep it clean. So if I could limit myself to sine, tangent, and secant, that's going to make life easier. All right? So I need this to come out of it, which is a sum of the squared values under the radical. The legs, exactly. So I would like my u to be the opposite side and my a to be the adjacent side, because that's going to create the tangent ratio. So tangent theta is equal to 2x over 1, or just 2x. I'll write 2x over 1, though. All right? You could put them the other way, but then you're getting a cotangent ratio. And when you do your substitution, you're plugging in a cotangent, which is a little bit more challenging to work with. Not the end of the world, but and still doable, totally. But do you want to do it? Probably not. All right. The square root of 4x squared plus 1 is the missing side. My secondary equation is going to be the ratio of the radical to the constant side. What trig ratio would that be?
Sine.
Not cosine. Radical to adjacent.
Oh, right up to adjacent.
Secant. It's hypotenuse over adjacent, so secant.
Drew, I love your confidence.
I said opposite over hypotenuse.
So tangent theta is equal to 2x, which means that x would be equal to 1/2 tangent theta. For the secondary equation, we're just solving for the radical. 4x squared plus 1 would be equal to secant theta. All right, so try finishing this one for homework, because I basically created all your substitutions. You just have to plug them in, simplify, integrate, and then reverse substitute.
You can have that.
I make it sound easier than it is, but it's still very doable. All right, so we needed to take the derivative of our x equation. This is the part where you start paying attention again. So dx is going to be 1/2 secant squared theta d theta. All right. That's going to require you to know some derivative rules, of course, but we've been talking about that for a while now. We know that we can swap out the radical for just a secant. So this is kind of ready to rock and roll, except you might run into an issue with the integral itself once you perform your substitution. So the dx gets replaced with a 1/2 secant squared theta d theta. The denominator gets replaced with just a secant theta. Now that whole thing simplifies down to 1/2, I'll put the 1/2 on the outside, just keep it clean, times the integral of secant theta d theta. So if you know the antiderivative of secant theta, you're like a step away from being done, which is great. Does anybody happen to know that one? If not, we have to create it using a fancy technique. We did.
Yes.
Because we stopped in the middle of a problem yesterday.
Molly.
The key indicator on that was when I said, we're going to continue with number 2.
I lied to you. Sorry.
It involves a secant tan. It also involves other stuff.
Is it secant squared?
Wait a minute.
That's not logic.
I keep guessing.
What's not logic?
Maybe it's a cosine.
It's a radical.
It's the anti-derivative.
It's the natural law of
There's a theta in there. And I'm so proud of you for coming up with that natural log all by yourself.
Natural log of secant tangent theta.
no
Plus tangent.
put the derivative?
I-
Secant
How would I
theta?
have known that?
I don't
Is
get
that a new rule?
It is a rule.
A new one?
Not new.
It's debatable as to whether or not it's new.
New for us.
No.
I'll show you where it came from in a minute.
Use
Maybe
the
like on the spot.
Oh, boy. Uh, 1/2 ln the square root of 4x squared plus 1. I believe that was the ratio. And then for the tangent, it's opposite over adjacent. So you're just looking for the opposite side of your theta, 2x over the adjacent, which is 1. So 2x over 1, which is 2x. Plus c. All right. That's the easy step at the end. After you've done all your substitutions and anti-differentiation, sometimes involving a rule, the one thing that should be very easy would be swapping back from trig form to algebraic form. And that's only contingent on the fact that you have an appropriate triangle labeled. If you have it labeled up, you're good to go. All right. So number 3. Again, we're trying to identify a u and an a. All right, so we're looking at, if you really consider this, I don't want to rewrite it just because I'm going to write it with radicals instead of fractional exponent. This has a denominator of 2, which means that there would be a square root radical involved. Right, so it follows the models associated with the trig substitution. So the u would be the square root of the variable component. So u would be equal to x, and a would be equal to the square root of the numerical component, and that's how we're going to build our triangle. Again, you really can't go wrong in building your triangle, because if you place your u and a in its incorrect location or incorrect locations, you'll find out pretty quickly once you use the Pythagorean theorem to find the missing side. You're like, oh, that's not what I wanted. All right, cool, so let me try something else. All right, so what I want to have is a sum of squares. So generally, that means that I want to have the radical as part of the hypotenuse. If there's going to be a subtraction, that's meaning that the radical should be one of the legs. All right, so that's telling me that my u and a values should be placed as legs of the right triangle. All right, so I'll put my u here, x, and my a here, and that'll give me the square root of x squared plus 1, or 1 plus x squared if you want.
It doesn't matter which leg you.
It doesn't matter. It doesn't matter at all, because what you're going to do, if you put the x here and the 1 there, when you create your ratio, you'll get the cotangent ratio instead of the tangent ratio, but that's not a big deal. All right. You could still work off of that. So tangent of theta. And also, if that happens, let's say you put the x on the bottom and the 1 on the side, and you get cotangent, you say, oh, well, I don't want that, so swap them and make it tangent.
Wouldn't it be x squared plus 1 under the radical?
X squared plus 1. Right, but it could also be x squared plus 1 under the radical cubed.
Oh, okay.
All right, so this is going to be tangent of theta equals x over 1, which is the same as saying x equals tangent theta. I know I have to differentiate this, so dx would be equal to secant squared theta d theta. The other part is always the ratio of the radical to the constant. Then you just have to decide what trig ratio that would be. Yeah, it's going to be secant. All right, it's hypotenuse over adjacent. All right, that gives us a direct relationship. It tells us that the square root of x squared plus 1 can be replaced with secant of theta. All right. So in this case, we have a dx on top, so secant squared theta d theta. on the bottom, I'm replacing the square root of x squared plus 1 cubed, all right? So the part that is the square root of x squared plus 1 is going to get replaced with a secant. So it'll be secant cubed. All of that's going to simplify down to what? In simplest terms. Which simplifies even further the cosine. Antiderivative of which is? Sine. All right, so then from my triangle, I just need a sine ratio, and I'm done. What's my sine ratio? Exactamundo. Sorry, there's a lag. Gotta start deleting some files. All plus c, and that's my integral.
Where did the cube
Where did the cube go?
Yeah.
This became secant cubed of theta, but then we divide the squared secant into the cube. Oops, it's not good. All right, next up, again, we have a radical component. It doesn't have to be on the bottom of the fraction. It could be on the top also. The variable component, take the square root, that's your u. The a is going to be the square root of the numerical components, in this case the radical 3. Create a triangle. Place your u and a appropriately to get the square root of x squared minus 3. All right. So where should the x go? Hypotenuse. All right. Now, if I'm going to create a ratio, a trig ratio that involves an x on top, so sine, cosine, tangent, cosecant, secant, cotangent, those are all the possibilities, but generally we want to stay with sine, tangent, secant. The x is the hypotenuse. Which of those functions, sine, tangent, or secant, has a ratio with a hypotenuse in the numerator? Secant. So secant of theta is really what I'm after. So that could actually steer you towards putting the radical 3 as the base. All right, if you put the radical 3 as the side here, the vertical leg, you would have come up with cosecant, not the end of the world, but then at that point you might say, well, I don't want to deal with that, so let me just put it on the other side and make it a secant. All right? So radical 3 on the bottom. Clean it up. X equals rad 3 secant of theta. So dx equals, it's a little beefier, radical 3, what's the derivative of secant? Secant x tan x, but in this case theta's. With a d theta at the end. All right. The missing leg, using Pythagorean theorem, would be what we're looking for, the square root of x squared minus 3. The ratio of that side over the constant would be the tan ratio. Opposite over adjacent. So tan of theta is equal to that. And now we're ready to do our substitutions, right? The good news is some things should clean up. It's not bad news, but it's not good news. We got that extra x there that we'll have to deal with. But that usually means that it'll help us clean up a little bit more than we might expect. All right, so on top, I have my radical, so that's getting replaced with a radical 3 tan theta. On the bottom, I just have an x. I'll deal with that in a sec. The dx is the same as radical 3 secant theta tan theta d theta. The bottom is the x. Now, if I'm going to integrate with respect to theta, every trace of x has to go away. Right? So that's fine. I just need a relationship that allows me to swap out this x. What would that relationship be? Rad 3 secant theta. That's right here. Okay, so sometimes you have to kind of hunt back towards earlier parts of the problem to see what an effective substitution might be. Okay? So some things cancel out, not everything, but some things. All right, so we're looking at a radical 3, I'll chuck that out in the front. Then tangent squared theta d theta. All right, so this is the big question in the problem. Do you know the antiderivative of tangent squared theta d theta? Now, on the formula sheet, we're looking at generally parent functions. Sometimes you have a little bit, different types of functions based on what you've learned from derivatives. So, like, we know tangent has a derivative of secant squared. So the antiderivative of secant squared is listed in the formula sheet because that's a consequence of something that you learned through differentiation. Not likely to find something like tangent squared theta. All right, so what that means is that you're going to have to use some knowledge of trigonometry to come up with that antiderivative. For example, an identity substitution. You could change it to sine squared over cosine squared, but you find very quickly that that doesn't really get you anywhere. The Pythagorean identity, we talked about this a week ago. Equals 1. If we divided each term by cosine squared, we get 1, by cosine squared, you get tangent squared plus 1 equals secant squared. If that's the case, a little corollary to that would be that tangent squared is equal to secant squared minus 1. And if you know that fact, and I don't mean this particular fact, I mean that sine squared plus cosine squared is equal to 1, and that you can do stuff to that equation. If you know that information, then you could always arrive at this. All right. So that's telling me that I can replace tangent squared theta with a secant squared theta minus 1. And what is the antiderivative of secant squared theta minus 1? Tan theta minus theta plus c. Now we just have to get rid of the thetas. So from the triangle, we can get our tangent ratio. That actually happens to be one of the things that we needed in order to make our substitution, so that's fine. We have the square root of x squared minus 3 over the square root of 3. That's the elephant in the room right there, the theta. And I'll get rid of that because I can't leave it in terms of theta. The answer's got to be in terms of x. Arc something. Arc secant of x over root 3. I like it. Yeah, any one of them. What do we say? X over root. So you have 6 trig ratios to play with here based on this triangle. You want to go for the simplest one, I would imagine. right? So 2 of them are listed here. If I were to take the inverse secant of both sides of this one, I get the arc secant theta equals the arc secant of x over root 3. If I use this one, I get theta equals the arc tangent of the square root of x minus 3 over the square root. That's disgusting. I mean, it's equivalently correct. I don't want it though. All right. You could go with cosine of theta equals the square root of 3 over x, in which case theta would be equal to arc cosine of the square root of 3 over x. You can pick any ratio from this triangle, sometimes ones that you didn't list out in order to create your substitution. If you find one that's more convenient, go with it and take that, right? You need to be kind of flexible with this because, again, multiple choice questions on the exam, what happens? You know, you come up with one that has an arc secant in it, but they chose the arc tangent. Then what? You know, if you don't know that they're equivalent to one another, then you move on from that question, never knowing that you could have gotten it right the whole time, and you just kind of bail on it. So that would be bad news. You don't want to do that. All right. So yeah, just pick your favorite ratio, at least when you have an opportunity in free response, and use that. Otherwise, just take a look at the choices and see what they went with, and then choose. You know, if they consistently went with arc tangent, it would be foolish for you to go with an arc secant at that point. Right? I think that's logical. Yeah.